Welcome to this lecture. This is the third lecture of week 1. In the previous lecture, we have introduced the concept of LP spaces. So, we have started off with some measure space or in particular probability space, and we have talked about classes of integrable functions there with certain order of integrability being required. Now, in this lecture, we are going to talk about some very specific properties of the norm function that we had introduced in this previous lecture. In this lecture, we are going to be focused on these very specific analytical properties of this norm function. Without further delay, let us move on to the slides. Before we start, let us set up the notation. So, we are working with this probability space or a measure space omega f mu, and on top of that, for p between 1 and infinity, 1 included, infinity not included, for such cases we are considering these classes of measurable functions defined on this domain omega taking real values such that their pth order integral is finite. And instead of working with a measure space, if you work with a probability space, then you end up with collections of random variables with pth order absolute moments being finite, being the required condition. Remember that we are always going to be working with p between this range, and we shall clarify the need for p being in this range a bit later. So, as said, we are going to be focused on certain analytical properties of this norm function, which will be in terms of certain inequalities. As you can recall, we have already talked about many of these inequalities in the introductory lecture, where we have talked specifically about the cases of random variables where these inequalities appeared in terms of their moments. We start this discussion by revisiting all those inequalities that we have already seen in the introductory lecture. More specifically, we are going to be focusing on Holder's inequality and the Minkowski's inequality. To start off with, we are going to be looking at the Holder's inequality, but stated in terms of this norm function. So, let us look at this. So, if you choose any two numbers p and q between 1 and infinity, please note we have excluded 1 here. Now, we want a relation between p and q to be of this form, that 1 by p plus 1 by q should be equal to 1. In this case, if you have a function f in LP and a function g in LQ, then the Holder's inequality says that the product function should be a measurable functions with this order of integrability, L1 integrability, and moreover the L1 norm of this product function can be dominated by the product of the individual norms, meaning the p norm of f and the q norm of g. For the random variables, the same inequality can be restated in this form. We continue with p and q as stated earlier. We take x such that it is in the LP space, y such that it is in the LQ space, then the product random variable should be in the L1 space with the L1 norm, which is nothing but the absolute moment of x times y, can be dominated by this product of these expressions, which is nothing but the product of the p norm of x and q norm of y. So, we have essentially restated the Holder's inequality that we have already seen earlier. Now, a special case of Holder's inequality is of interest. This we have already pointed out as part of corollaries in the introductory lecture, but now we are going to be restating them in terms of the p norm. This inequality is called the Cauchy-Schwarz inequality. So, again, as done earlier, we are going to be stating two versions, one for the measurable functions and one for the random variables. So, let us say I take two functions f and g in L2 space, then the inequality says that the product must be in L1 with the L1 norm of the product function dominated by the product of the L2 norms of f and g. For the random variables, the same inequality can be restated. Take any two random variables x and y in L2 space, then the product random variable is in L1 space with the L1 norm of x times y, which is nothing but the first absolute moment of x times y, is dominated by the product of the L2 norms of x and y. Now, it is a important question to answer, that we have so far stated inequalities here. So, when does this equality hold? So, under what special conditions on x and y, for example, the equality will appear? In theorem 5, which is the general Holder's inequality, and corollary 4, which is the Cauchy-Schwarz inequality. Please check them. We now move on to look at further applications of the Holder's inequality that we have stated, and this is part of the next remark. So, the first thing that we note, that the degenerate random variable, which is identically equal to 1, or restated as, take the degenerate random variable supported at 1, then by exercise 2 earlier, this random variable is in LQ for any q in 1 to infinity, 1 included, infinity excluded. In fact, we can actually show that the q norm of y is exactly equal to 1. Now, you fix a real number p between 1 and infinity, exclude 1, and set q to be this expression, which is p by p minus 1. In this case, what will happen, that this equality, which is 1 by p plus 1 by q equal to 1, this relation will be satisfied if we choose q accordingly like this. Then for any x which is in LP, what we can show by Holder's inequality, by choosing y to be identical equal to 1, that expected value of x actually equals the L1 norm of x times y, because y is identical equal to 1, but then apply the Holder's inequality and end up with this bound, that this is exactly the pth norm of LPth norm of x. Therefore, what we are essentially saying, if you start off with a LP random variable x, then its first absolute moment turns out to be finite, which is of course also the L1 norm of x. Therefore, if you take any x in LP, it is also in L1, and since x is arbitrary, you actually conclude that LP turns out to be a subset of L1. Now, this inclusion that we have just shown actually works in a more general setting, and here this probability measure can be replaced by any finite measure. So, let me restate the result. This inclusion will continue to work if I replace the probability measure p by any finite measure mu. Now, we are going to be generalizing this previous statement, from which is the inclusion between L1 and LPs, to a more general cases of P and Q satisfying this range. Now, here what we need is that we start with a LQ random variable z and choose a random variable x this way. There is a minor correction required in the notes here, which will be done in the final lecture notes supplied to you. So, here we are choosing capital X to be mod z raised to the power p, and choosing r to be this ratio q over p. By the choices of the two numbers p and q, the number r turns out to be greater than 1. Now, as can be immediately seen that x is in L of r, since mod x to the power r, the expected value of that is exactly mod z to the power q, the expected value of that, which is given to be finite. So, therefore, x is in L of r. Now, applying the part 1 of this remark, we conclude that x must be in L1, and therefore, expected z to the power p, now rewritten in terms of expected mod x, we can apply the previous inequality that we have seen, that turns out to be the rth norm of x, which is nothing but the expected mod z to the power q raised to the power p by q. Now you rewrite these relations with appropriate powers on both sides and we end up with this relation, which is what we wanted, and this actually shows that Z must be in LP. So what we have end up showing is that for any arbitrary Z which is in LQ, it must be in LP whenever P is less than Q. Therefore, we have managed to show that LQ of P must be contained in LP of P. This is generalizing the previous statement when we have been able to show that LP was contained in L1. So here you have to note that P and Q must be in this range. Now a special case of this last inequality that we have managed to show is the following. So we can choose P equals to 1 and Q equals to 2. Then for any x in L2 we have x in L1, and moreover the L1 norm of x is dominated by the L2 norm. But note that this inequality that you see here, which is the first moment being less or equals to the square root of the second moment, this is a familiar inequality, and this also appears in the discussion of variances of random variables. Recall that variance of x has two known expressions, one in terms of the definition, which is the second moment x minus expected x, the second moment of that, and another equivalent expression for this is the difference of these moment expressions, second moment of x minus the square of the first moment. But since this expression here is non-negative, you end up having the inequality that the first absolute moment of x is less or equal to square root of the second moment. We now move on to discussing certain further important properties of these LP spaces. You fix P between 1 and infinity, choose any two functions f and g from this LP space, then the proposition states that f plus g must also be in LP. This is a very important result, and we are going to be seeing its application in the further discussions. So we first start by looking at the measurability of f plus g. Since both the functions f and g are measurable, by standard algebraic properties of measurable functions, we immediately conclude the measurability of f plus g. Now to complete the proof, we need to show this integrability condition that modulus of f plus g raised to the power p, that integration of that should be finite. But our given information is that modulus of f raised to the power p and modulus of g raised to the power p both have finite integrals, and therefore to conclude our result, it is enough to establish an inequality of this form that modulus of f plus g raised to the power p is less or equal to some constant times modulus of f to the power p plus modulus of g to the power p. If we establish this inequality for some constant, positive constant, then just by taking integration on both sides we will be able to explain our result. Therefore, it is enough to establish this more deterministic type inequality. Now for illustrative purpose we are going to be doing this in two different methodologies, and both will give us certain interesting ways of estimating these functions. The first method goes like this. You first start with modulus of f plus g raised to the power p. Observe that modulus of f plus g is less or equals to modulus of f plus modulus of g, and therefore the first inequality follows. But then each of the functions here is less or equals to the maximum of these two. So therefore each of modulus of f and modulus of g is less or equals to the maximum, and therefore you end up with an additional 2 here. But then you raise it to the power p, so you get this exact equality which is 2 to the power p, and the power p function is continuous and it will go inside the maximum. But then the final step goes like this, just by observing that the maximum of these two functions must be less than the addition of these two functions. Because we are dealing with non-negative quantities, the maximum of these two must be less than the addition. And hence we have arrived at the inequality of the type we wanted, that modulus of f plus g raised to the power p must be less than some constant which turns out to be 2 to the power p by this method. We now apply another method and obtain a different constant. In this method, what we observe first is that we have chosen our p to be greater or equals to 1, then the function x going to x to the power p defined on 0 to infinity is actually a convex function. In this case, what you do is that you look at modulus of f plus g raised to the power p, start with the same expression and apply the same inequality at the beginning, that modulus of f plus g is less or equals to modulus of f plus modulus of g. But now you manipulate this by dividing and multiplying by a 2 inside the expressions. So, therefore, outside you will get an additional 2 to the power p, but then apply the function x going to x to the power p being convex, and hence you immediately have this expression by the convexity of the function with an inequality here. Therefore, after simplifying all the expressions here, you end up with the type of inequality that we wanted, but with a constant which is now 2 to the power p minus 1. Remember, in method 1 we ended up with 2 to the power p, but in method 2 we ended up with 2 to the power p minus 1. Either method works because both will give us the integrability of mod of f plus g raised to the power p, and this will complete the proof. Now, as seen above, in these two methods that we have applied, method 2 is going to provide us a sharper constant than method 1. So, we should always keep track of such methods which gives us better inequalities. Now, it is an important thing to keep note that there are these two propositions that we have seen. Proposition 3 was talking about scalar multiplication on LP. Proposition 4, which we just discussed, is talking about additions in LP. Therefore, if you combine these two results and do standard verifications, it will immediately follow that LP of mu, and in particular if you use a probability measure, you will end up with LP of p. In either cases, this will turn out to be a real vector space. Now, you have a linear space at hand, and on top of that you have this norm function that we have introduced. We are now going to be revisiting another important inequality that we have seen in the introductory lecture. This is the Minkowski's inequality, which was stated in theorem 2. Remember that we had stated this earlier only for the random variable setting, but of course this is also true for the measurable function setting. But now, since we are working with a linear space which is LP, here we can think of this Minkowski's inequality as a triangle inequality for this norm function. So, let us see this. So, we are going to be fixing this p between 1 and infinity, 1 included, infinity excluded, and we are going to be choosing any two functions f and g in this LP space. Then the inequality says that the p norm of f plus g is less or equals to the addition of the p norms. Now, the Minkowski's inequality as seen here holds if p is between 1 and infinity in this very specific range. However, if you choose p between 0 and 1, a positive real number between 0 and 1, then it actually does not hold, and it is for this reason we will work with p in very specific range, which is this 1 to infinity, rather than working with all positive p. Now, we are going to be consolidating all the properties of the norm function that we have seen so far. So, this is the next important result, which is proposition 5. So, as we have already justified, we are going to be working with p in this range. Now, the function that we have been calling as a norm is actually satisfying the properties of a norm. So, let us restate it, that we have associated for every function f in the LP the p norm of f, but this function actually satisfies the standard properties of norm, and this is justifying calling it a p norm. So, let us see the proof. As we will see, we have already done the preparation. In remark 2 earlier, we have identified through almost everywhere equalities and the equality in P norms. Recall that P norm being 0 is implying and implied by F identically being 0. This equality F equal to 0 should be understood in the sense of equality of equivalence classes. So that property of a norm function is satisfied. The second one is about scalar multiplication. So if you choose any scalar alpha in the real line and a function in the LP space, then the P norm of alpha times F is mod alpha times the norm F. This property is also satisfied. This property of a norm is also satisfied. And finally, Minkowski's inequality, as we have already stated, is actually the triangle inequality for this norm, and therefore this completes the proof that norm P satisfies the important three properties of a norm function, and this justifies calling it a norm. And together with this observation, we end up with the observation that LP of mu together with this norm function is now a normed linear space. Moreover, given any two elements f and g in this LP space, we have a natural distance function given by this metric by the P norm of f minus g. Now with this distance function, we can describe neighborhoods of elements in LP. So we can describe neighborhoods, we can describe open sets and end up with a metric topology. So as soon as we have a normed linear space, we have a natural induced distance function given by the metric, and with this metric we end up with metric topology. Now we can work with this metric topology and talk about many continuous functions, and this immediately follows that the norm function that we have been talking about is actually a continuous function in this topology. So let us see the proof. So for any two functions f and g, we already have that norm of f. I can rewrite this expression in this form, that f is actually g plus f minus g. Now apply the Minkowski's inequality or the triangle inequality and end up with this relation. But rewriting this relation gives us the difference of these two norms is less or equals to norm of f minus g. Now if we exchange the roles of f and g, we will end up with the other side of the inequality, which is the difference of norm of g minus norm of f is nothing but norm of g minus f. But since this norm is symmetric, this is nothing but f minus g is p norm. Therefore, combining all these observations that we have seen so far, we end up with the observation that modulus of p norm of f minus p norm of g is dominated by the p norm of f minus g, and therefore it immediately tells you that as long as the right hand side quantity is small, this left hand side quantity also has to be small. Therefore you immediately have the mapping f going to norm of f is continuous. We are actually going to be stating further such continuity properties involving all the operations that we have observed so far. Let us start with the addition operation. Take any p between 1 and infinity, then the addition function, which is going from LP cross LP to LP by taking any pair of functions f and g to their addition, is continuous. The second one involves multiplication. Choose any two p and q between 1 and infinity. We are excluding 1 here with the choices that 1 by p plus 1 by q has to be equal to 1. In this case, the product operation, which is going from LP and LQ to L1 by taking this pair of functions f and g to their product pointwise product f times g, has to be continuous. Let us see the proof. To prove the continuity of the addition operation, we use the Minkowski's inequality. To see this, take functions f g, f tilde, g tilde and look at this difference. from f plus g and f tilde plus g tilde. Then rewriting this by applying the triangle inequality or the Minkowski's inequality, we end up with the addition of these two norms. But whenever f tilde is close to f, the first term can be made small. Whenever g tilde is close to g, the second term can be made small, and therefore the left hand side, which is coming from the addition operation, has to be small. Therefore, we can make, by choosing f tilde and g tilde close to f and g, we can make the addition operation continuous. So, this is now stated more explicitly here. So, just to be clearly stating the epsilon and delta differences as we justify for continuity, we are going to be choosing f tilde close to f by this distance and g tilde close to g by this distance. Then consequently, the term that we want can be made smaller than epsilon. A similar argument works for the product operation, and for this we use the Holder's inequality. To see this, let us look at this expression fg minus f tilde g tilde. Here we first manipulate this expression and rewrite using this expression, that f times g minus g tilde. So, we have subtracted f times g tilde here, and therefore we have to adjust it in the other term. So, that we have done, and therefore we end up with this expression. Now, by applying first the Minkowski's inequality or the triangle inequality, we end up with this summation of these two norms. But now we apply the Holder's inequality, therefore you end up with this product of the p norm and the product of the q norms. Now, here we have to make this left hand side term to be small. To do this, first you fix an epsilon positive and choose f tilde and g tilde in this specific manner, that f tilde should be close to f by this order and g tilde should be close to g in this order. So, these choices has been made explicitly so that norm of g tilde turns out to be this plus this, and by manipulating all of this together, what we can show now that the term that we want can be made smaller than epsilon, and hence this is going to be ensuring that this can be made arbitrarily small, smaller than any epsilon positive that we choose. This essentially proves the product operations continuity, and this completes the proof. As a final comment, we restate the Markov's inequality that we have seen so far in the setting of LP spaces. So, take any f in LP and choose epsilon positive. Then the measure of the set where mod f is exceeding epsilon is exactly equal to measure of mod f to the power p exceeding epsilon to the power p, that can be bounded by 1 by epsilon to the power p times p to the power of p norm of f. So, measure of mod f exceeding epsilon can be dominated by 1 by epsilon to the power p times the p power of the p norm of f. And in the next lecture, we are going to be discussing about certain convergence of sequences in LP. Remember, we have so far shown that LP is a norm linear space and therefore carries this metric topology coming from the norm. Therefore, we can talk about continuity properties as well as convergences. This is what we are going to be discussing in the next lecture. Thank you.